Hey guys, Miss Marusik here, and in this video we're going to talk about the connection between Gibbs free energy values and equilibrium constant values. Now, as a reminder of some of the things we've talked about in our recent videos, we have been discussing Gibbs free energy and doing calculations with it to solve its value. And what we've said up to this point is that if delta G is negative for a particular reaction, then that process is thermodynamically favorable. It's spontaneous. It's likely to occur without any significant outside help. However, if the delta G of a reaction is positive, then that reaction is not thermodynamically favorable, meaning it's not a spontaneous process, and it would require an input of work or energy to occur. Now, notice I didn't say here just heat, and I want to make that very clear because heat would just be an enthalpy change. Here I'm talking about delta G, so I'm talking about a work change, which could include heat, but it could also include other forms of energy, meaning that I could force these reactions to happen by adding some sort of external source of energy. For example, I could add electricity to it, I could add light energy, but some sort of work that doesn't necessarily have to be heat. The other way I could force these reactions to occur is, as we talked about in our previous video, I could couple it to another favorable reaction. And what would happen is when I couple those together, if the overall process ends up favorable, that can force that unfavorable step to occur in that overall process. Now, something to also clarify here. If that forward reaction is not thermodynamically favorable, what that means is that the reverse reaction would be thermodynamically favorable. If I could flip that process around, then it would spontaneously occur on its own. Now, Gibbs energy is all about if that forward process is likely to happen. And if you think back to a previous unit, there's another time that we've talked about measuring how much a forward reaction is likely to occur. And that was when we talked about equilibrium constants. Now it says here Kc, but really you could also use this with a Kp if you had gases. So let's first talk about a Kc greater than 1. If I have an equilibrium constant greater than 1, thinking about the fact that equilibrium constants are products over reactants raised to their coefficients, being greater than 1 would mean your numerator is greater. We would say that there are more products at equilibrium, or that the equilibrium was product favored, which means the forward reaction is proceeding in a significant amount. I'm making lots of product. So what that means is that our forward reaction is favorable. And so therefore we should see a negative delta G value when we have a Kc that's greater than 1. Now, if a reaction has a Kc value that's less than 1, thinking products over reactants, less than 1 would mean that the reactants, the denominator, is bigger, and so that means we are reactant favored. Our reaction is hanging out more on the reactant side instead of going over and making products. So that means that forward reaction is not favorable anymore. It would actually rather stay as the original reactants. And so what that means is that we would see a positive delta G value when our Kc is less than 1. So notice there's that relationship between the Kc value and what kind of sign we're seeing on our delta G value. Now, to see this in action, you have a table down here that shows you some various values for the delta G and the corresponding K. Okay, so you'll notice here that here's our breakpoint between being positive and negative for delta G. So looking at the positive end of things, you'll notice that our Kc values get really, really small. So again, those tiny K values would mean that I'm not making much product, that essentially I'm sticking on the reactant side. And the smaller we get, meaning the larger negative exponent, then we basically are not doing any forward reaction whatsoever, that all of it is sticking on the reactant side. And again, notice what's happening to that delta G. It's becoming more and more positive there. So again, a positive delta G would mean that we have a K that's less than 1, but remember, it can't be less than 0. It can't be a negative value, so that's why I put that it falls between 0 and 1, and that would be not favorable in the forward direction. However, as the delta G gets negative, notice my K's are getting bigger and bigger and bigger. And the bigger it gets, then that means the more we're going towards completion, the more we're going to the product side of things. So that forward reaction towards the products is becoming more and more favorable. And so what that means here is that a negative delta G would have a K value that's greater than 1. Now, to see some of these in action with actual reactions, let's look at the table that's right below this. And what you'll notice on here is that we have two reactions given to us where they've given us both the delta G value of that reaction as well as the Kc value. Now this first reaction here should look familiar. We have liquid water going back and forth between hydrogen ions and hydroxide ions. And hopefully we remember that this is the self-ionization of water. But most of water, 99.999% of it, is going to stick together as this H2O. Very little of it is actually going to make ions. So now, notice your delta G value. It is positive. So from a thermodynamic standpoint, we would say that this reaction is not favorable in the direction written, in the forward direction. Our Kc value, hopefully this value looks familiar. That's that Kw that we recognize for water. And we notice that it's really, really small. We have a negative 14 there for our exponent. So being very tiny, that would mean that from an equilibrium standpoint, we would say that this is reactant favored, which again makes sense because we said most of this is going to stick on the reactant side. So I do want to warn you, even though we see the double arrows here, we're always going to be referencing these in terms of the forward direction. Now, what that would mean is that if I flipped this reaction around, if I went reverse, that both of these values would become more favorable toward the products. So keep that in mind that these values are only when written in this forward direction here. Now we see this same kind of idea with the nitrogen gas, hydrogen gas synthesis to make ammonia gas. We notice that we have a delta G value here that's negative. So that means it is a favorable process from a thermodynamic standpoint, meaning it should be going to the products. So I should be making lots of products. So again, then think about if I'm making lots of products, what kind of K value would I see? Well, we should see a K value that's greater than 1. And in fact, we do. It's a fairly big K value here. And so again, that would indicate that this is product favored. So in this forward direction, we're going to be occurring a significant amount in that direction. Now, I do want to remind us, just because a reaction is favorable or not favorable, so just because it's reactant or product favored, that tells us nothing about the speed of the reaction rate. So we have to be really careful. Just because I'm favorable, just because I'm product favored, does not mean that that reaction is going to happen fast. It all depends on what the kinetics are of that particular reaction. So just be careful there. Being favorable does not necessarily mean it's fast. Those two things are very different. Now, you notice back from this table up above that there's a ratio here happening between the Gibbs and the K values. Like there's a mathematical ratio that's occurring there. And that ratio is related by this equation that you see down here. That delta G, so the Gibbs energy change at SATP conditions, at standard conditions, would be equal to the negative RT ln of K. And I have really good news for us. If you look at your formula chart, That is the next equation we have on here for delta G. So we've already talked about the fact that delta G, I could use the Gibbs of formation of products minus reactants. We've also looked at this delta G equals delta H minus T delta S. So this is just another equation that we can use to help us with delta G. But now we see K being used. And again, this K is going to be referencing the equilibrium constant expression. You could see it used within equilibrium calculations. So you might be doing like a Rice table calculation where you actually calculate K. And then once you calculate K, you could plug it in here and solve your delta G. That's a really common thing that you could be asked to do. However, more frequently than not, you are given a delta G value and you're actually asked to find the K. So that means you're going to have to undo that ln there. So we'll talk about undoing the natural log here in just a little bit. However, you do notice R in here. And this is the same R that we used with gas constants. So if you go up to your gas constants, you'll notice 3 options here. However, think about this from the perspective that we're trying to do a thermodynamic calculation here. And so I would want to use one of these that includes maybe something like kilojoules or joules in it to use with thermodynamics. So you notice here that we're only going to be using this first R value here. That first R value has joules in it, divided by moles times Kelvin. So they've done it with the -1s, but that's the same thing as joules per moles times Kelvin. So that's the only R value that we're going to be using for these problems. However, I do want to point out that that R value has joules in it. And most of the time, our delta G is going to be in kilojoules. So you're going to have to be really careful with matching up your units here, or it's going to be really easy to mess up your decimal point on these. Okay, so just be careful on those units. One last thing, more often than not, your temperature is going to be at standard conditions. It's going to be at 298 Kelvin, unless somehow otherwise stated in the problem. So with that said, let's go ahead and flip the page and see how we would do some of these calculations. All right. So we are given here an equilibrium reaction. We see our double arrow there. And they have given us over here some thermodynamic data. They have given us some delta G of formation values. And the first thing they want us to do is to determine the delta G value for the reaction with the information that we've been given. So again, this is where I would say to myself, I see delta G of formations. That might mean I'm using this lovely equation right here, our products minus reactants equation, right? And so that's what I've done here. However, you should be taking into account your coefficients. Remember, these are only per mole of the substance, and we want this to come out in terms of moles of the reaction. However, in this reaction, everything had a 1-to-1 ratio, and so therefore all of your coefficients ended up being 1 in here. So really, you didn't have to show them here, but I went ahead and did just to double check and make sure that I'm not missing anything. And so when I did that calculation here, that got me a positive 218.1 kilojoules per mole of the reaction. Now, I'm going to pause here for a second. Think about what we already know. We already know right now that this had a positive delta G. Would that be favorable or unfavorable? Well, I hope we know that means it's unfavorable, right? And so if it's unfavorable, that means you're not going to be really going all that much to that product side in this reaction. Most of it is going to stay as a reactant. And actually, the reverse direction would be, in fact, more favorable. So we know already that if I'm not making much product here, that my K should be less than 1. So now when I do this next calculation here, I'm going to be double checking to make sure that that K comes out less than 1. So let's talk about the next calculation. What they want us to do is to determine the Kc, the equilibrium constant value for our reaction. And so I'm going to use our new equation of delta G equals negative RT ln of K. And we know that our R value, the only one we're allowed to use for this type of problem, is the 8.314 joules per mole times Kelvin. Now we have to be careful here. This is joules, right? Well, look at your calculation up above. This was in kilojoules. Why? because this table was in kilojoules. So you got to be really careful here with your units. You have to make these units match up when you're plugging in. And so what I did is I took this kilojoules value and changed it over into joules. Now, could you take this joules and change it into kilojoules? Sure, you could do either way. You just need to make those units match. If you don't make them match, it's not going to come out. Okay, so again, I took kilojoules, converted it into joules. There's 1,000 joules for every 1 kilojoule. So I should see a lot more joules here. I should be moving that decimal over 3 places for that 1,000 ratio between them. So then, I just set up the rest of this problem here. I'm assuming 298K because I know I'm calculating a standard here. And what our goal is going to be here is to solve this K of the equilibrium constant. Now, I went ahead and wrote units here for a couple reasons. First off, it helped me to double check to make sure units match. But I want to show you what happens with your units. Joules and joules cancel. Moles and moles cancel. Kelvin and Kelvin cancel. So your K ends up without units. But remember, K does not have units to it. So that makes sense. All those other units should cancel their way out. Now, what I would do here math-wise is I would take this 218,100, divide over negative 8.314, and then divide over 298. And what that gets me in my calculator is a negative 88.0297. However, that's still going to equal the natural log of K. The way to undo a natural log is to raise both sides with these values to the e. So like you have e raised to the negative 88, you have e raised to the negative ln of k. And what that e will do is undo the ln. So you end up on this side with just k. Now if you're unfamiliar with where your e key is at, this is different e key than when you're doing exponential form. You want to do the second button and then this ln where you see e to the x above it, okay? And so that'll put this in your calculator that then you can go plug in that negative 88.0297. Or if you had the previous answer in there, you could do e raised to the answer, and that might be a little faster. So here's the value I got, okay? I got k equals 5.88 times 10 to the negative 39. Well, let's think about this for a minute. We said our delta G was positive, that this is not favorable. We said K should come out smaller than 1, and look at there, it comes out way smaller than 1, right? And look how tiny that value is. It's super small. So what that means is that we're making very little product in this reaction. It is heavily reactant favored, meaning the reverse reaction is way more favorable than this forward direction. Now, the next question is kind of interesting. It asks what would be the equilibrium concentration of CO2. So think back to this reaction here. If I was to write a Kc expression, remember solids as well as pure liquids don't get included in a Kc expression. So that means that this BaCO3 would not get included. And this BaO would also not get included. Your Kc expression would literally be just CO2. Now here's the deal. It's products over reactants, right? So it's just that CO2 for the Kc expression. It looks kind of weird, but that is the Kc expression. So if you wanted the molarity of CO2, it would be the same here as the Kc. Now, that's not always the case. Okay, keep in mind that sometimes you might actually have to do an equilibrium calculation to figure this out. But this one was pretty easy to figure out based on the values. I did go ahead and put a unit of molarity since I was calculating the concentration here. So the next question asks, is this reaction above thermodynamically favorable in the direction written? Justify your decision. Now, we've already talked about in this unit one way we could answer this question. We can look at our delta G value. And we know that the delta G is positive, and so the reaction is not thermodynamically favorable in the way that it's written. But now we have a second way that we could justify this. You could also justify by saying that the Kc is less than 1, and that would mean that it's more reactant favored, and so it's not favorable in the direction that's written from a thermodynamic standpoint. All right, now these last two questions here are kind of a throwback to some things that we've talked about previously. On E, it asks, what would be the Kc value if the reaction was reversed? Well, remember, when I reverse a reaction, what that will do is it will inverse the Kc value. I'll do 1 over the Kc value. And that will end up getting us 1.70 times 10 to the 38th. Now notice how incredibly large that is. Heavily product favored here, right? But now we flip that a reaction around. So it should be heavily product favored. If the original reaction was heavily reactant favored, then the reverse should be heavily product favored. Now it also asks what would be the delta G value if the reaction was reversed. Now I know we haven't talked about changing signs on delta G a whole lot, but it works the same way as it did with delta H. With enthalpy, if I reverse the reaction, I would flip the sign of the delta H. And so I do the same thing here with delta G. So reversing this, instead of a positive 218.1, I end up with a negative 218.1. Now, notice both of these are favorable. This is greater than 1. This is a negative delta G here. So the reverse reaction was more favorable from that standpoint of both equilibrium and from a thermodynamic standpoint. All right, with that said, here's what I want us to do. On the next page, you will notice a series of questions. Now, all of these questions are things that we have answered previously in other units or earlier in this unit. And so what I want you to do is to take a moment and pause the video and try out this example. All right, did you pause it? Did you try it out? Okay, let's check and see how we did. So the first question said, hey, the Kc for this reaction is 1.12 times 10 in the negative third at 750 Kelvin. Using no math, just logic, would you expect the value of Kc to increase or decrease at 298 Kelvin? Well, notice we're talking about a lower temperature. So we know that the Kc value will change. Equilibrium constants change when I change the temperature. And so I need to think about this heat. Notice that heat was on the reactant side. This was an endothermic process. So being endothermic, if I decrease the temperature, that means I'm removing heat out of this. And remember, I always shift towards what I remove to replace it, thinking Le Chatelier's principle. So that would cause us to shift to the reactant side. So if the reaction is endothermic, decreasing temperature would shift the reaction to the reactants. And so for shifting towards the reactants, our value of Kc should decrease. Now, what we're doing in these next several questions is we're going to prove that that is in fact the case. So the next thing they want you to do is to determine the delta H value for the reaction. They gave you a whole bunch of heats of formations up here. By the way, you notice that Cl2 and O2 both had heats of formations of 0. Again, because those are elements by themselves in their standard state. And so that's why they were 0. And so you really didn't need to include them in here, but I went ahead and put them in there anyway. However, you did have to, on your other substances, address your coefficients. So hopefully you remember to do that when you did products minus reactants. That should have gotten a value of a positive 114.4 kilojoules per mole of the overall reaction. So we can see that it in fact was endothermic as expected by seeing that heat value there. Okay. All right. The next question said determine the delta S for the reaction. So again, thinking about my formula chart, I have all those S values up here, all those entropy values. And so if I take the products minus reactants of those values, I can get the overall entropy change. And so that's what I've done here. Again, make sure you address your coefficients. So when I did products minus reactants, I made sure to multiply each of those entropy values by their coefficient. That got a value of positive 109.3. And my unit here, looking at the units up above, would be joules over Kelvin times mole of the reaction. Now notice, delta H is positive, it's endothermic. That's not great. However, the delta S is positive, and that is good. Endothermic is not great to have, but A positive delta S is good. We like having more entropy. So next we need to see whether or not this is thermodynamically favorable. It might be or it might not be. It depends on the temperature here, since one thing was good and one thing wasn't. So looking at our delta G here calculation, this is what we did in a previous video. We said that delta G equals delta H minus T delta S. Now you do have to be careful here and make sure your units match up for your entropy and your delta H. Now, you could have these both in kilojoules. I know we did that in a previous video. What I actually did is put them both into joules. So I converted the delta H from kilojoules into joules. And I'll explain why I did that here in a minute. You didn't have to. If you did it in kilojoules, that's fine. But in any case, I came up with a positive 81830 joules. Now, if you did this in kilojoules, you would have gotten a positive 81.83 kilojoules, okay? Again, either answer would have been appropriate as long as you showed a unit with your answer. Now, notice that did come out positive. So that means this is not thermodynamically favorable, right? Most of this is going to stick as the reactants and very little is going to make products. What does that mean about our K value? We should be seeing hopefully a really small K value, right? Something less than 1. So we'll find out here in a minute if that was the case. By the way, because it was endothermic, but we did have a positive S value, what that would mean is that in order to get this to be favorable, we would need a really large temperature here. So unfortunately, this temperature was just not large enough in order to get it to be favorable. And I want to kind of show you how, from an equilibrium standpoint, that kind of makes sense. If I want to drive this reaction more to completion, okay, if I want it to be more favorable in the direction written, then if I crank up this heat, if I increase the temperature, I shift away from what I add, and so that would shift me to this product side here. So at a higher temperature, I should be favorable in the forward direction because that would get me toward the product side here. So that ties back to what we've talked about previously, that when we have a positive delta H and a positive delta S, it's only favorable when that temperature is really high. Now, I know that was a little bit extra than what you had to do here, but I thought I would go ahead and talk about that since we're actually seeing the mathematical application of that thought process. So finally here, they wanted us to calculate the Kc, the equilibrium constant value for the reaction at 298 Kelvin. So we did delta G equals a negative RT ln of K. Now, remember back here I said I did this in joules for a reason, right? Well, the reason why I went ahead and did it in joules is because I remembered that right here, when I use R, that's in joules. And I need my G to match that. And so that's why I went ahead and calculated up here in joules. So then that saved me a conversion down here. So as long as you're making sure those units match, it really doesn't matter what unit you're using. You just want to be really, really careful here with making them all match. So then it was just doing the calculation just like we did previously. So what I would do is I would divide over the negative 8.314. I would divide over the 298. That gets a negative 33.028 equals ln of K. I do E raised to our number would equal K, and that ends up getting a K value of 4.53 times 10 to the negative 15th. Now it asks here, how does this value compare with your prediction? Remember, back up here, we said that if we use 298 Kelvin, okay, that we should see the value of Kc decrease. It should be smaller than 10 in the negative third, right? Well, let's see if it's smaller than 10 in the negative third. Well, look what we're getting now. We're getting 10 in the negative 15th. That's smaller. So that's good. It matched up with what we predicted using Le Chatelier's principle. So as crazy as this is, it's actually proving the point here that as you decrease that temperature, you should see that decrease in K if you had an endothermic reaction. It's actually proving mathematically that point. Now the last question here says, is this reaction reactant favored or product favored? Well, obviously we just calculated the K value here. It's way less than 1. And so that means we are reactant favored. But the other way we knew that we were reactant favored even without calculating the K is that the delta G was positive, which means that it is not favored in that forward direction. So most of it should be staying as our original reactants. All right, I hope we're feeling good about making all of these connections between Gibbs energy, Le Chatelier's principle, equilibrium constants. I mean, we've kind of run the gamut here of connecting all of these old things together. It's kind of crazy how this really pulls it all together. But if you have any questions or need any help, please feel free to email me. Bye, guys.